Okay, let me start by acknowledging my collaborators. So this is joint work with student faculty at USC, especially Brandon Paulson, who is a former student of mine, and he's a driving force behind this work. So first, let me start with the motivation. So we know that machine learning is making a big impact, especially on autonomous systems, from transportation, manufacture to healthcare and agriculture. So much of this is fueled by progress in deep learning. For example, the use of deep learning for accurate object identification and also for high performance control. However, much of these applications are safety critical, which means that if deep learning fails, then there can be catastrophe. Since I work in this area called formal verification, so we're mostly concerned with this question. Can we prove that a deep learning model always behaves safely? And to answer this question, we have to answer two sub-questions. First, how do we define this verification problem, the safety problem? And second, how to efficiently solve it? So in this work, we focus on a subset of the verification problem. We call it differential verification. So in the next few slides, I'm going to give you two example applications for differential verification. The first example application is neural network compression. And people usually train the neural network, for example, using 32-bit edge weights. But before implementing it on real devices, they try to compress it to either reduce the energy consumption or to reduce the computational cost. And this is very similar to how people use compilers to optimize the machine code. Now, there is this natural question. After this compression, how do we know that the compressed network faithfully mimic the original? If given the same input, they should always produce the same output, or at least the difference between the outputs should be bounded by a very small constant, right, an epsilon. So this is one example application. Another example application is called sensitivity analysis. This is when neural networks are used to generate, for example, steering directions of a vehicle based on sensory input. So here our interpretation is that a vehicle shouldn't zigzag abruptly, right? Instead, we expect it to have a nice, smooth trajectory to the destination. So this, again, can be viewed as a differential verification problem. You have the same neural network, two different executions, but with slightly different sensory inputs. And you want to bound the output difference. So this is differential verification, but it turns out to be a very difficult, and it was a previously unsolved problem. So a few years ago, when we started working on this, we were not aware of any prior work targeting this particular problem. I think much of the difficulty is coming from the fact that neural networks are treated as black boxes. So they may have thousands or sometimes millions of parameters inside. They are difficult to interpret. And because of this black box nature, there are many hidden misbehaviors inside the neural network. So that's why we wanted to develop techniques for automated differential verification of deep neural networks. Now, I want to talk a little bit about related work. Although there were no prior work on differential verification problem, there were some closely related work on testing and verification of a single neural network. Here, I'm only listing some of the early papers, so there are a lot more, including some of the recent papers from the CMU teams. So what's the problem with testing? The main problem is it doesn't provide formal guarantees, which are kind of important for many safety critical applications. So that's in general what motivates people to work on verification. But existing work on verification also has a limitation. So they're designed primarily for a single neural network. But in differential verification, we are concerned with two structurally similar but behaviorally equivalent neural networks. So a natural question is, can we use current verification tool to solve this differential verification problem? You can imagine that you have these two neural networks, you try to merge them and by feeding the same inputs, and then at the output layer, so y and y prime, you can take the difference, y double prime equals y prime minus y, and you expect this y double prime to be 0 or very close to being 0 for all possible inputs. So that's actually the first thing we tried. We built this composed network and fit it to some existing tools. It didn't work. So there are these two reasons. The first one is that the current verification tools are not accurate enough for solving this differential verification problem. So when they propagate the input all the way to the output and take the difference, usually the result is so inaccurate, it's not going to be very useful. And the second problem is that these existing tools are not general enough in the sense that they can only handle certain activation functions. So that's why we started developing techniques for accurate, for making this differential verification more accurate and more general. So that's pretty much the motivation of our work. So in the next few slides, I'm going to briefly talk about the limitations of the prior work. And from that, I'll talk about our high-level ideas. Without getting into the details, I want to first show what our high-level ideas are. And then I'll talk about the technical background and then details about our work. So there are two limitations for this existing tools. The first one is accuracy, or the lack of it, when they're used for solving this differential verification problem. So here again, we have this composed network. We have the first neural network on the left, second neural network on the right. We can take the difference and we can feed the same input. And the expectation will be that the y double prime should be 0 or very close to being 0. However, if you use existing tools, what happens is that each of these two neural networks will be analyzed in isolation. And during the process, there will be a lot of approximation errors. So when you take this abstraction, the errors gets carried over and the result is going to be very imprecise. So that motivates us to come up with some new ideas. And the first idea that we came up with is that we actually should try to approximate the difference early on, instead of waiting for the error to be propagated to the output layer and then take the subtraction. At that moment, it will be too late. Instead, what we want to do is we want to compute the delta on each individual pairs of neurons at the input layer, and then start propagating the difference, the delta, layer by layer. And so hopefully by the time we reach the output, the errors are not accumulating. So the key insight is that we should start approximating early before significant errors accumulate. So we've evaluated this idea, and it turns out this is very effective. We can get anywhere from 10x to 1,000 times accuracy improvement. And so this we published in 2020 in a paper we call it ReLU. So in addition to that idea, we have another idea, which is the use of more accurate symbolic approximation during this forward analysis. And so the key idea is that instead of propagating the concrete values through these neurons, we want to keep them as symbolic expressions, right? So we use symbols to try to capture the dependency information between the values of different neurons. And that would allow them, the symbolic terms, to be to cancel at the later layers. So that can give us another 10x accuracy improvement. So this was another paper that we published in early 2020. So that's related to the first limitation. The second limitation of the current tool is generality, or the lack of it. So in order to illustrate this, I have to talk about something called activation functions in neural networks. So neural networks use these activation functions inside the neuron. And the commonly used ones are ReLU and sigmoid. So these are the things that current verification tool can handle very well. And what happens is usually some domain experts would have to sit down and handcraft the linear approximations for each type of activation function. And the currently good ones are, for example, ReLU and to some extent sigmoid and TAM. And the idea is illustrated by the figure on the right-hand side. And you can see that this is the activation function within a certain range, input range. You want to use, for example, linear functions to bound the actual function. So these handcrafted linear approximations are actually very difficult to design. We have the existing tools being able to handle ReLU and sigmoid, but there are a lot of state-of-the-art activation functions being discovered very, very frequently. And for all of these complex activation functions, then somebody would have to sit down and design the linear approximation and then implement it in the verification tool. And that's complicated. And there are even groups in industry, for example, Google Brain, try to automatically discover activation functions. So for all of those newer network architecture, they wouldn't be able to benefit from this nice formal verification tools. So that's what motivated us to come up with some techniques to automatically synthesize the linear approximation. So give us an arbitrary activation function, something that we haven't seen before. If it's possible for us to automatically come up with a sound upper and lower bounds for this activation function, then we can plug it into the verification tool. So what we realize is that in many of the prior works on single neural network verification, that linear upper and lower bounds are quite effective. So that's why we focused on synthesizing linear upper and lower bounds for this new activation functions. And we think that might be benefiting our differential verification also. So we also published 2 papers last year related to this automated synthesis of linear approximations for arbitrary activation functions. So that's pretty much my high-level overview of this talk. Without getting into any technical detail, hopefully you get a sense of what we're working on. So I wonder if there are questions at this moment. Otherwise, I would start with the technical details.
Are there any questions?
Okay, so I'll start. What I will do is I'll first talk about the basics of neural networks very, very briefly, and then I'll talk about some of the techniques underlying the single neural network verification, and then I will talk about the baseline differential verification before introducing our own technique. So you can view the neural network as a function that would take some real valid inputs, x1 and x2 here, and then return a real valued output, y. So what happens inside is that the inputs, in this case, x1 and x2, are first multiplied by the edge weights, in this case, -1, 1.11, and 0.9. And then the result is going to be summed up, and that's the input to the activation function. And the next thing is to take the activation function. In this case, it's ReLU, so on the right top corner, which returns the max of 0 and the input expression x. So once you apply this ReLU, and then you will generate the input for the next layer. You just keep repeating, and then you will generate the result. So that's a neural network in a nutshell. And next, I'll talk about how do people verify neural networks. So far, the most scalable approach is this thing called symbolic interval analysis. So this is a general technique that has been used very widely in the verification of numeric programs for many decades. But recently, people started applying similar techniques for neural networks. So this has been used a lot in single neural network verification tools. Again, here I'm listing some of the earlier papers. And this technique is the basis of our work. So I'm going to briefly talk about them in the next 3-4 slides. I should mention that there is another type of technique called constraint solving based analysis. But it's very different from the things that we're using. So I'm not going to talk about it here. So let's again take a look at this neural network. And what people do is to first come up with a symbolic interval for the inputs. So in this case, neuron n0, the input value is represented by this interval from x1 to x1. So that's the lower and upper bound equations. Initially, they are the same, which means that there is no approximation error. And then you start propagating the intervals through this neural network. And eventually, when you reach the output, you would have, again, the lower and upper bound. So a times x1 plus b times x2 plus c is the lower bound expression, and ex1 plus fx2 plus g is the upper bound expression. So the neural network verification tools usually would guarantee that this inequality holds, which means that the actual output value should always be enclosed by this upper and lower bound. And using the upper and lower bounds, you can prove a lot of interesting properties. So you can actually use this idea to try to solve differential verification, the problem. So that's what I call here the baseline. So again, you would have these two neural networks, F and F prime. So let's just imagine that F prime, you got it by rounding the edge weights. For example, on the left-hand side, you have minus 1.1, you round it to minus 1, right? So that's one way of creating this differential verification problem. Now, the question is, how do you prove that they are behaving the same for all inputs? So the property is specified as the difference at the output is less than or equal to 0.15. And that is for all inputs. And so that's basically a very classic example of the differential verification problem. And the baseline differential verification can be thought of as propagating the symbolic inputs over these two networks in isolation. So you propagate it on the left-hand side and on the right-hand side, and then you try to take the subtraction. But as I mentioned earlier, there will be a lot of approximation errors introduced. By the time you're at the output layer, it's too late. So in this case, at the output layer, you want to try to show that the difference is always bounded by 0.15. Now let's see why this doesn't work very well, right? Here on the right top corner, I'm showing you the actual parameters for this propagation. So let's say on the left-hand side, take the interval from the input layer, and you multiply the edge weights. So that would be the result. That would be the input at at N2, and we expand it a little bit. That's the upper and lower bounds. So at this moment, because there are only linear operations, so there is no approximation error, and this is actually a very accurate lower and upper bound. But then you would have to take the ReLU, which is nonlinear. And here you are forced to introduce approximation errors. The reason is because you want the result to also be linear. You don't want nonlinear expressions because that will cause the explosion of the expression. Now, how do you get a linear upper and lower bound for this nonlinear function, right? Between minus 1.1 and 1.1, that's clearly nonlinear. So you actually want to have a linear upper and lower bound, like this is cx plus d and ax plus b. So the key here is to come up with this coefficients for this particular case. And then you plug it in, and then you would have this linear upper and lower bound for the output of N2. For output of N3, you do the same, and then eventually you would come up with the upper and lower bound for N4 and N4 prime, and then you take the subtraction. So this is where, again, you're going to introduce errors because the resulting upper and lower bound are going to be lower minus upper and upper minus lower. So you would get a very loose bound because the actual difference is actually between 0 and 0.1. And you can see how loose the bond is. So pretty much is useless. This is why the baseline differential verification does not work very well. And the reason is everywhere along the forward propagation, you're introducing errors. So the error accumulating. So that brings me to our first big idea, which is to approximate the difference, the delta, early on, and only propagating the delta layer by layer from the input to the output, rather than propagating the absolute values. So here, again, the baseline approach would wait until the end to take the difference. What we want to do is to take the difference early on, everywhere, at every pairs of neurons. So here is what we are actually doing. So we define this delta, the difference between N0 prime and N0. So this is N0, this is N0 prime. The difference initially is from 0 to 0, means that there is no difference at the very beginning. And similarly for N1 prime and N1. So let's call them delta 0 and delta 1. So that's the difference interval. Then what we want to do is propagate this difference interval layer by layer. And we just need to focus on one neural network. We're considering the other one implicitly. So in this case, the first technical difficulty is how do you propagate the difference interval across layers, right? Because previously it was the absolute value, that's straightforward. But now you have to be careful because you're propagating the delta. The second technical difficulty is how do you apply the activation function, the nonlinear function, to this delta interval? Again, it's not that straightforward because now you have two neurons. Basically, you're trying to bound the difference between two ReLU. So for the first technical difficulty, we solved it this way, right? We realized that the delta, the difference at the next layer, would depend on two things. The first thing is the delta in the previous layer. And the second one is the difference between the edge weights. So that can be actually captured very accurately using this equation. So the delta from the previous layer times the edge weight, and then the absolute value from the previous layer times the difference of the edge weights. So we proved that this is sound, and then we implemented it. So now you have this delta 2, which is the input upper and lower bound before the ReLU. So this computation is actually very accurate at this moment. But then you would have to take the ReLU, which is nonlinear. And in this case, it's much worse because it's ReLU N2 prime minus ReLU N2. So you actually have two variables instead of just one variable. And that's complicated, right? You could solve this very naively by saying, okay, I'm going to compute a symbolic upper and lower bound for the first term and another one for the second term, and I'm going to do the interval subtraction, lower minus upper, upper minus lower. Yeah, you can get a bound, but then this is not accurate at all. So what we want to do instead is to directly bound the result of this delta. And here, this is basically a two variable non-linear function. So there are actually 9 different cases. So based on whether the upper and lower bound for the first one is always positive or always negative, or one of the lower bound is negative, upper bound is positive, which we call unstable. So you have 3 different cases for the first term, 3 different cases for the second term. 3 times 3 is 9. So what happens is that for each of the 9 cases, we can sit down and take out a piece of paper and try to come up with a sound upper and lower bound. So we did that. So at runtime, you don't have to think about this. Just identify which of the 9 cases is it, and then apply a predefined linear approximation. So that's how we are able to handle this kind of difference over this ReLU. And in this case, for N2, the result is going to be minus 0.1 and 0.1. So we did that for N2, and then we do the same thing for N3, and then we start propagating it to N4. So that's how we get a much more accurate bound at the output. So that's basically at the high level how our method works. Of course, you could do better than this. And one of the ways is using refinement. So the idea is that if you feel that this result is still not accurate enough, what you can do is you can split some of the input regions. So in this case, we say that X1 is between 0 and 1. But if that's not accurate enough, you could split it into 2 verification sub-problems. So the first one, X1 is between 0 and 0.5. Second one is between 0.5 and 1. If you can verify for each of the sub-problem that the difference at the output is bounded by a small epsilon, then you're done. But if one of them is still not conclusive, then you could further split the input intervals. Obviously, here you can imagine that the main thing is the heuristic for splitting the input, because which input variable to split, that's the big question. So we came up with some heuristics for choosing the input to split. And this is based on counterexample guided refinement. Basically, in the in terms of neural network, it's using the difference at the output layer to try to compute the gradient, over the inputs, and then try to figure out which one to split. So it's very similar to back propagation. So that's the first technique that we proposed. We evaluated this on some neural networks from the literature. So these are the 3 benchmarks: the air collision, the aircraft collision avoidance, the MNIST, and also the third one is the human activity recognition. You have some smartphone, and based on the sensor data, try to predict whether the user is sitting or standing or walking or running. So in total, we have 842 equivalence verification problems. So what we did is apply our method and also 2 single neural network-based verifiers. So these were earlier work. We were using ReLU Val from Columbia, and then this DeepPoly from ETH Zurich. And you can see that we are able to verify 332 more this differential verification problems. So our tool is actually always faster because it's focusing on the delta. And for more than half of these problems, the speed up is actually between 100x or 1000x. So that's the first idea. And just to recap, the idea is to try to focus on the delta and propagating only the delta terms instead of the absolute values. And we want to do this as early as possible, because that can drastically improve the accuracy. But the question is, can we do better? So that brings us to the second idea, which is to try to use more symbolic approximations. during the computation of the difference, the delta terms. So here, remember that in the previous example I showed you, for N2, the bond that we computed is actually a constant. And this is not because we don't want to keep it symbolic, like on the right-hand side. It's because we are forced to do this. And because of this, these constant values are getting propagated to the next layer. And this is bad because it doesn't allow terms to be canceled at the next layer. And if we can somehow keep them symbolic, the symbols are propagated to the next layer, then they will be able to cancel. And the reason why we cannot do this for N2 is because we were trying to approximate this, the output of this function. And remember, we were using this 9-case analysis, and it turns out that the result is a constant upper and lower bound. And we studied the reason why this happened. And one way to explain this is to try to show the output of this function in the 3-dimensional space, because we're having these 2 variables, right? N2 and delta 2. So we can imagine this N2 is the x-axis, the delta 2 is the y-axis, and the z-axis will be the result of this function. So this will be the shape of the function. And what happened is that this linear and upper and lower bound we are computing are actually 2 horizontal planes that are bounding this function. And you can see clearly here, right? The upper and lower bound. But is this the best upper and lower bound? No. And you can see that if you tilt the planes slightly, you would have tighter upper and lower bounds. So these are what we call the linear approximations instead of the constant upper and lower bound. And in fact, mathematically, you can think of it as A times N2 plus B times delta 2 plus C. So all you need to is come up with the appropriate A, B, C, and E, F, G, right? So again, we did that. We just did that manually and then try to come up with a more accurate linear approximation. And when you plug this in, what happens is that the output of this delta 2 will become symbolic. And you can see that there is this symbol called x2 here. And on the right-hand side, you also have x2 here. So when both of these terms are propagated to N4, they cancel. And that's how we improve the accuracy. Of course, this is not the entire story, because you can see that, in this case, you would get much more accurate bounds. But this is not the entire story, because there are still some constant here, like minus 0.05, right? So even for that, we could have some tricks, right? We could introduce some new symbols to represent this minus 0.05. So if it gets propagated along multiple paths to the next layer, then they would still have a chance to cancel each other. So that is basically the second thing that we've proposed. So we implemented that, we compared it with our ReLU approach and on the same benchmarks, and we were able to observe a significant accuracy improvement. And you can see that there are 97 more differential verification problems being solved by this approach. So to recap, what we're proposing are some very, very carefully crafted upper and lower bounds for this differential term. And it actually conceptually simple, but you'd have to come up with the approximation proof that it's always the sum, and then you implement it, and then you do the experiments. So in total, it took us more than 6 months of time to finish this. But this is just for ReLU. I imagine that what if the activation function is a sigmoid? We didn't do this, but I suspect it will take another 6 months. But then what about other activation functions? There are many novel activation functions being proposed very, very often. And for each of them, probably we have to sit down and do this study. verification and then evaluation, right? We didn't want to do this. This is too much work. What we want to do is, this brings me to the second idea in our work. We want to automatically synthesize these linear approximations instead of handcraft them. So the motivating example, for example, in many neural networks, you would encounter this kind of activation. It's a sigmoid of x times x. So this is a curve. What you really want is like between this L and U, between these two regions, you want a tight linear approximation. Upper bound ax plus b, lower bound cx plus d. And the question is, how do you do that? You either handcraft it and then you implement it in your tool, or you do this automatically. So we want to do this automatic, right? So in the following few slides, I'm going to focus only on the upper bound, ax plus b. But before I keep going, I want to point out that during the verification, the L and U may change. It could be any value. So really, although ax plus b, a and b are two coefficients, they are the constants. But a and b are actually functions themselves in terms of L and U. So what you're actually computing is a huge lookup table called the GLU. Give me the L and U, which could be anything in real verification. And you need to have the A and B, the coefficients, ready. Now, before we solve this problem, we actually found that there are some existing solutions. So one of them is from actually the CMU team. I don't know how to pronounce this tool. We call it AutoLipra, but I don't know if that's the way to pronounce it. But this is a very interesting idea. So in order to get a linear bounds for sigmoid of x times x, you can use the existing linear approximations for sigmoid of x. So that's available. And you also know how to handle multiplication. So once you have upper and lower bounds, and you can, of sigmoid of x and x, you could assemble them together, again, using interval multiplication, right? So, but the problem of this approach is very similar to the previous things that I discussed. So you've accumulating approximation errors. So by the time you compute the result, you may have a very loose bound. So what we want to do instead is to just synthesize these bounds for this particular activation function as a whole instead of assemble them together. So that's our idea. And before I talk about our method, I have to talk about what's the definition of a good approximation, right? Usually people would define it as minimizing the volume between the upper bound, ax plus b, and the activation function, which is this curve. So this shaded area, the volume should be minimized. So that can be captured accurately by this nonlinear optimization problem, minimizing the volume subject to this activation function is always less than or equal to this linear bounds, upper bound. So you could actually conceptually solve this using some nonlinear optimization tools. And the problem is that this is going to be very expensive. And remember, you need to do this at every neuron during the verification. So this is kind of very expensive. So what we did instead is to propose a much cheaper way of doing this. So our idea, which we call it online synthesis, is to turn this nonlinear optimization problem into a linear optimization. So this is approximation. If we can solve this, then we get a bound. It may or may not be a sound or approximation, but we can actually verify it. If it's a sound approximation, we use it. Otherwise, we try to tweak it. So that way it's much cheaper. And the way we relax it is based on this intuition that in this whole nonlinear optimization problem, this delta, I mean, the activation function is the only nonlinear part. So if we can get rid of this, we can linearize it. And the way we do it is by sampling. We would sample some points along this nonlinear function, and then we replace this nonlinear function with the concrete values of the sampling points. These are constant. So if these are constant, the rest of the problem is linear. So that's how we get a relaxed solution. Very, very quickly, we were able to compute this upper bound. Now, this upper bound may or may not be sound. So how do you define sound? So you can see the violation is the difference between the two, right? If it's bigger than 0, then you're smaller than 0, or you're in trouble. So we're using a tool called the derail, which is a nonlinear SMT solver to verify it. So if the verification fails, then we try to shift the upper bound up a little bit and then verify it again until we get a sound bound. So that's what we call this online synthesis, because the synthesizer is calculating things by invoking the LP solver and then SMT solver at every neuron during the verification. So this will be very accurate, but it also has the computational overhead. And subsequently, we try to move this computation offline, which means we pre-compute this big lookup table GLU offline. So at runtime, we don't need to call any solver. Instead, we just plug in the values. So that we call the offline synthesis. So here is a very brief comparison of this tool. Online synthesis try to invoke the solvers to compute A and B at runtime. Very accurate, but has overhead. Offline synthesis is synthesizing A and B offline, but so it's fast, but it's less accurate. So we implemented both. We try to compare them. So here is the result. So we're using this AutoLIRP as the baseline. So without our technique, it's able to solve 90 differential verification problems. But with online and offline, they're both solving a lot more problems. And the online solves more, which means the online is more accurate, but offline is usually 10 to 20 times faster than online. So that's pretty much what I want to talk about. Again, the summary is that there are 3 big ideas. The first one is to focus on the delta, approximating the delta early on, and propagating the delta layer by layer. And the second one is to use more symbolic approximations during the forward propagation. And the final idea is about automatically coming up with this linear approximations instead of handcrafting them. So, for future work, one thing that we want to do is to close the gap between the online and the offline synthesis. And you can see that there is still a significant difference here. And we are also interested in these other types of approximation, right? Right now, we focus on only the linear upper and lower bound, but in many verification tools nowadays, you're using some other, polyhedral, like Zonotop, or some other. Sometimes are using nonlinear approximations. So those will be interesting future work. Another related work is to automatically repair the verification. Suppose we are not able to prove that these 2 neural networks behave the same, then is it possible to modify the second neural network to make the verification go through? So that will be another interesting direction. So I'll stop here and say if you have any questions.